The puzzle has gaps. The picture around each gap gives clues about what's missing. Modern imputation uses those clues, the observed data, to predict the missing values, while properly accounting for the uncertainty in those predictions. KNN Imputation finds the k most similar complete observations based on the observed features, then averages their values for the missing feature. If patient A is missing a lab value but has similar age, weight, and other labs to patients B, C, and D, use the average of B, C, and D's values. In single-cell RNA-seq, MAGIC uses a diffusion-based approach. Construct a king graph of cells, then smooth gene expression across neighbors. Cells with dropout zeros borrow expression values from similar cells where the gene was detected. Mice multiple imputation by change equations is a gold standard for clinical data with multiple variables having missing values. For each variable with missingness, specify a regression model using all other variables as predictors. Predict the missing values plus random noise. Cycle through all incomplete variables. Repeat the entire process m times, typically 5 to 20, producing complete datasets. Each dataset has different imputed values reflecting the uncertainty. The magic is in the chaining. Each variable's imputation benefits from the most recent imputations of every other variable. Rubin's rules combine the M analyses. The pooled point estimate is the average across the M analyses. Pooled variance combine two sources, the average with an imputation variance, the usual uncertainty, and the between-imputation variance, the extra uncertainty from not knowing the missing values. The between-imputation variance is multiplied by 1 plus 1 over m. More imputations reduce this correction factor. The pooled confidence intervals are wider than they would be with complete data, correctly reflecting the information lost to missing S. The M algorithm takes a model-based approach. The E step, given current parameter estimates, compute the expected value of the missing data, fill in the gaps using the model. The IM step, given the filled-in data, re-estimate the model parameters using maximum likelihood. Iterate until convergence. The IM algorithm never explicitly imputes values, it integrates over the missing data. All information maximum likelihood goes further. It maximizes the likelihood of the observed data directly, using each patient's available observations without imputation. Both is SUM-MAR. Single-cell RNA-seq dropout is a specific form of manner. Lowly expressed genes fail to be captured by the sequencing technology. SVI models this with a zero-inflated negative binomial distribution, the restaurant counters ZIN. The zero-inflation component explicitly models the dropout rate as a function of the mean expression. SAVER uses a Bayesian framework to predict true expression from observed counts. scImpute distinguishes true biological zeros. The gene genuinely isn't expressed from technical zeros. The transcript was present but not captured. Each method requires a different model of the missingness mechanism. Know the mechanism before you impute. MACAR is rare and easy. Complete cases work. MAR is common and fixable. MICE is the gold standard for clinical data. MNIR requires explicit modeling of why values are missing. ZINB per scRNA-seq Dropout. Selection models for informative censoring. Simple methods are almost always wrong. Rubin's rules properly account for imputation uncertainty. Fill the puzzle, but know which pieces fell and why.